Assalamualaikum kanak-kanak Nabina, and hello. We'll meet again in Electromagnetism 4.1 part 2. Okay, so saya nak sambung apa benda yang saya dah terang ke awak before this in the first video. Okay, kita dah sembang pasal catapult field. Kita dah tengok catapult field produce a force, right? Okay, so that force yang produce dekat catapult field tu, dia di-effect oleh ada dua benda yang utama, which is first current and second is strength of magnetic field itself. Okay, so untuk current, this one permanent magnet magnetic field dekat permanent magnet. Okay, so untuk current, the greater the current akan jadi the greater the force, because bila current lagi banyak, so the temporary magnetic field pun akan jadi lagi kuat, so therefore force yang produce akan semakin kuat. Okay, so ingat the higher the current, the higher the force. Okay, same goes here. Strength of permanent magnetic field pun kena high, barulah current kita, force kita pun akan jadi high. Okay, akan jadi lagi besar. Okay, untuk strength of magnetic field, kita boleh ubah dua benda dekat the magnet untuk increase the strength of magnetic field. Satu, kita ubah dia punya distance. Okay, lagi dekat distance antara these two permanent magnet, contohnya north dengan south kan. So kalau dia orang lagi dekat macam ni, lagi kuat dia punya strength of magnetic field. Okay, kalau jauh kurang dah sikit. Size of magnet pun sama, lagi besar magnet tu, lagilah kuat dia punya magnetic field strength. Okay, so that's two factors, main factors. Okay, so kalau kita buat eksperimen, kita akan nampak the more the current flow, the wire ni boleh ditolak lebih jauh. So kalau sikit je, banyak tu je lah dia boleh tolak. So this represent the force. Okay, so the larger the force, the larger the current, the larger the force, lagi jauh lah benda ni akan tertolak. Okay, samalah juga dengan kalau kita dekatkan these two magnetic poles, kita akan produce stronger magnetic field and kita juga akan produce larger force. Jauh juga dia boleh ditolak. Okay, ni salah satu eksperimen yang kita boleh buat lah. Ada juga eksperimen yang dia measure jarak antara jauh tak this conductor boleh pergi. So conductor ni dia akan bergerak. Kenapa dia bergerak? Sebab kita dah sembang tadi ada force yang akan produce when kita ada current flow. Contohlah current flow ke sana. Okay, so using awak punya left hand rule, kita nampak kita punya force akan produce ke sana. Okay, nanti saya tunjuk cara untuk guna Fleming left hand rule to determine the direction of the force. Okay, so kalau awak guna Fleming left hand rule, awak akan mendapati bahawa this conductor will be moved to the right. Okay, because of other force yang produce lah. Okay, so kalau dalam eksperimen tu dia akan kira jarak. So lagi jauh jarak dia boleh pergi, maksudnya lagi kuatlah force produce. Okay. Okay, now kita dah belajar catapult field, dah belajar semua. Kita nak tengok pula, tadi kita belajar untuk straight wire kan, forces untuk dekat straight wire. So apa jadi kalau kita ubah this straight wire into a coil? Okay, bila saya sebut coil, maksudnya kita ubah bentuk dia. Tadi bentuk straight wire kan, sekarang kita nak ubah dia jadi bentuk macam ni. Ni salah satu contoh coil. Okay, and then kita nak letak coil ni dalam magnetic field. Apa jadi? So now, ni contoh dia lah. Contoh kita ambil coil, kita letak dalam magnetic field. Yang ni current flow. Okay, ni I. Yang hitam punya arrow ni adalah current flow. Okay, so part ni current flow ke depan, part ni current flow ke belakang atau ke bawah. Magnetic field macam biasa, north to south. Okay, so north to south. Saya nak guna colour lain lah. Sekejap. Okay, kita guna kali hijau untuk magnetic field. Okay, so magnetic field from north to south, maksudnya daripada kiri ke kanan. Okay, ni magnetic field. And then current pula ke depan. Okay, satu ke belakang, satu ke depan. Okay, kita label lah dulu ni A, B, ni C, ni D. So, untuk AB, first kita cari dulu force untuk AB. Okay, guna awak punya Fleming left hand rule. So, kita punya magnetic force ke apa benda? Ke kiri. Kita punya current ke depan. Jadinya force produce akan jadi ke atas. So, untuk side AB, force produce akan jadi ke atas. Side CD, bila kita guna Fleming left hand rule, kita akan mendapati force produce dia ke bawah. Okay, so satu ke atas, satu ke bawah. Bila ada dua forces yang berbeza macam ni, satu naik atas, satu turun bawah, kita akan produce satu we call as turning force. Okay, turning force ni dia akan bergerak lah. Dia akan satu atas, satu bawah, dia akan turn jadi nanti tunjuk macam dia turn jadi straight macam tu. So, dia punya movement is clockwise. So, movement dia akan jadi clockwise. Kalau satu wire je, kita tengok satu force je, sama ada atas atau bawah. Tapi kalau ada coil of wire, dia ada dua side yang berbeza current flow dia. Kita akan ada force ke atas dan force ke bawah. So, dia akan turn. Okay. This thing, the coil will turn clockwise. In clockwise direction lah. Okay. Okay, now mari kita tengok video on the turning force. Okay, video ni dalam bahasa Melayu. So, faham je lah kan. Oh, sebelum tu. Apa pula? Okay, ni kalau lukisan lah. Lukisan catapult field. Tapi sama je. Kalau awak tak nak lukis, kalau awak tak erti guna left hand rule, awak boleh lukis. Okay, tapi susah lah. Bukan susah. Renyah lah sikit. Sebab nak kena tengok dulu direction of the ni kan. Yang mana yang sama, yang mana yang tak sama. Renyah sikit. So, kalau tak nak guna catapult field produce ni, kita boleh je guna Fleming left hand rule. Okay? Okay, now the video.
Kesan putaran gegelung pembawa arus dalam medan magnet. Pertimbangkan sebuah gegelung ukuran ABCD yang disambung kepada bekalan kuasa arus terus. Gegelung itu terletak di antara kutub-kutub magnet bekal. Bekalan kuasa arus terus mengalirkan arus dari terminal positif ke terminal negatif, iaitu melalui gegelung dalam arah A, B, C, D. Sisi gegelung AB mengalami daya magnet ke atas. Arah daya itu ditentukan dengan menggunakan petua tangan kiri Fleming. Sisi gegelung CD mengalami daya magnet F ke bawah. Pasangan daya F menghasilkan kesan putaran pada gegelung itu. Dan gegelung itu berputar. Maka gegelung pembawa arus dalam medan magnet mengalami pasangan daya magnet F yang menghasilkan kesan putaran pada gegelung. Kesan putaran ini merupakan prinsip kerja bagi motor arus.
Okay, so nampak macam mana bila kita letak coil dalam magnetic field, macam mana dia punya mechanism. Okay, so I hope you understand that one. Tu baru satu. So now, daripada situlah kita boleh build one thing nama dia DC motor. Okay, motor ni selalunya kita guna untuk anything yang perlukan rotation. Okay, I mean like benda yang nak menggunakan pusingan lah, macam kipas, macam apa lagi, apa-apalah yang memerlukan rotation. Okay, so now DC motor dia ada dia punya kompartmen-kompartmen dia lah, parts dia. Kompartmen pula, dia punya parts. So first kita ada commutator. Commutator ni apa? Commutator ni kita connect commutator dengan kita punya coil. Kita punya coil, okay, dia sejenis conductor lah juga yang boleh mengalirkan elektrik. So kerja dia ialah to reverse the direction of the current in the coil every half rotation. Macam mana dia reverse nanti saya terang. So that the coil ni akan continue to turn in some direction. Maksudnya kita nak buat dia satu putaran, okay. Kalau dia tak reverse the direction, awak punya coil akan jadi kiri kanan, kiri kanan, kiri kanan. Dia tak boleh nak buat 360 degree punya rotation. Okay, dia boleh buat 180 degree sahaja. Kita tak nak macam tu. For a complete rotation, kita nak dia 360 degree rotation. Right? So, itulah kerja commutator. Okay, carbon brush, dia untuk alirkan arus elektrik dalam coil of wire. Carbon brush ni dia yang connect dengan power source. So, dia akan in contact je. In contact doesn't mean dia orang melekat bersama, no. Dia macam sentuh je commutator tu. So that dia bolehlah alirkan current dekat the coil of wire. Okay. Spring, tugas dia untuk push the brush to always contact with the commutator. Okay. Dia nak tarik tolak macam tu je lah. Tugas spring kat situ. Okay, so how DC motor works? Okay, first, okay, kita akan melihat another video. Melihat another video. Okay, this video.
Now, we are going to discuss about working principle of DC motor. The working principle of DC motor is very simple. We know that when a current-carrying conductor is placed inside a magnetic field, it experiences mechanical force towards a particular direction. Let's take a simple elementary model of a DC motor. In this model, one single turn of conductor is placed between two opposite poles, that is North Pole and South Pole, as shown here. Now, if we start...
Okay, before that awak kena imagine dulu side ni dia macam side A, B, C, D. Okay, sebab later tak apalah, imagine dulu dia orang ialah A, B, C, D. Alright, don't change the side.
Supplying DC through a commutator system to the single turn, current starts flowing through it. At that position, as we see, the positive terminal of the battery is connected with left conductor of the turn and negative terminal of the battery is connected with right conductor of the turn. Moreover, we see here in the model, the south pole of the magnet is placed at left side and north pole of the is placed at right side. Current in this left side conductor flows inward and current in right side conductor of the turn flows outward. As we see, the conductors are carrying current and placed inside a magnetic field. Both of them experience mechanical force acting on them. The direction of the mechanical force can easily be determined by applying Fleming's left-hand rule. For that, we have to stretch forefinger, second finger and thumb of our left hand at right angle to one another. With that, if the forefinger is aligned along the direction of magnetic field, that is from North Pole to South Pole, and second finger or middle finger is aligned along the direction of current in the left side conductor, then thumb indicates the direction of mechanical force. This is clearly upward here. Similarly, again, if forefinger is aligned along the direction of magnetic field, that is from North Pole to South Pole, and second finger or middle finger is aligned along the direction of current in the right side conductor, then thumb indicates the direction of mechanical force. This is clearly downward here. Due to these upward and downward forces on the turn, one torque is produced, which tends to rotate the turn in clockwise direction as shown.
Okay, now at this position sekarang ni kita punya kita punya side dah berubah. So sekarang ni B kat sini, A kat sini, C and D kat bawah lah. Okay, yang tak nampak tu. This is the position now. Okay, notice that sekarang ni kita punya carbon brush ni dah tak touching the commutator. Okay, dia kat tengah-tengah ni, meaning kat tengah-tengah ni kan tak ada apa-apa, tak ada commutator. So meaning tak ada current flow at this position. Okay, bila dia turn 90 degree, tak ada current flow.
At position, there is no current in the conductors of the turn, as the conductor end brushes rest in between two commutator segments. Hence, there is no force acting on the conductors, but due to moment of inertia, the turn continues to rotate and comes horizontal again.
Okay, so dekat sini maksudnya tadi kenapa dia jatuh balik? Sebab adanya inertia. So sekarang ni kita punya side dah berubah. Dia jadi macam ni Tadi ABCD belah kiri, sekarang tadi AB belah kiri, sekarang AB dah jadi belah kanan. Okay?
But position of the conductors has been interchanged here. That means the conductor which was previously at left position comes to right position, and which was previously at right position comes to left position. At that position, again mechanical force acts on the conductors, whose direction can again be determined by applying same Fleming's left-hand rule. Let's do that. For that again, we have to stretch the forefinger, second finger and thumb of our left hand at right angle to one another. With that, if forefinger is aligned along the direction of magnetic field, that is from north pole to south pole, and second finger or middle finger is aligned along the direction of current in the left side conductor, then thumb indicates the direction of mechanical force. This is clearly upward here. Similarly, again if forefinger is aligned along the direction of magnetic field, that is from north pole to south pole, and second finger or middle finger is aligned along the direction of current in the right side conductor, then thumb indicates the direction of mechanical force. This is clearly downward here. Due to these upward and downward forces, the turn tends to rotate in clockwise direction as shown. Now from that explanation, we can come to the conclusion that here in this model, whichever conductor comes under south pole experiences an upward mechanical force, and whichever conductor comes under north pole experiences a downward mechanical force. And due to these two forces, the single turn continues to rotate until the battery is disconnected. A practical DC motor rotates with same principle as of this elementary single turn model. Practically, in a DC motor, in place of single turn, there is multi-turns armature coil, and in place of two poles, there may be more than two, even number of poles. Hope you understood. Thank you.
Okay, so dia thank you, saya pun thank you lah juga. Okay, so that is how a DC motor works. Okay, I hope you understand all the mechanism. Okay, dia akan keep on going lah dia punya rotation tu, sebab tu dia boleh rotate. Okay, that's that for today I guess. So semoga faham. Kalau tak faham, tanya, okay, komen kat bawah ke apa benda ke, PM saya ke, you do know my number, right? Okay, so that's all. Thank you. Bye. See you soon.